Since yesterday morning, we are witnessing that seeing all these pre-engineered, prefabricated, composite structures and all that. So, and about also a green building concept. Actually, if we go back to 3,800 years, during the period of Mahabharata and all that, Lord Krishna had to offer his childhood friend Sudama some house, and he ordered Vishwakarma, and just overnight for Sudama, that Sudama Nagari was created just in span of 10 to 12 hours. The whole village was constructed like that. When the Pandavas they were traveling and when they were staying, halting, so during night they used to have all those caves and all that. Of course, we see the structure, but we don't know really whether it was just in a night or what. But it can be an inspiration for us, no? Actually, we started from M33 to M63 and all that cement, then FE415 to FE750 with ductile and all that. All these things are there, and all the mechanization and everything is there. But of course, the time saved at higher cost and all those things are there. Why not any Vishwakarma come out from us? Why not there is any cloning technology? Just copy and all that. As Surya Prakash had said, can we have a off-the-shelf house? Just go buy a house and erect it at home, at your plot or something like that. Can we not have something like that? Can we not think in that direction so that just the whole, all the components of my house, I can purchase and take it in an auto rickshaw and just go and erect the house. It may look funny, but only the foolish and silly ideas get to inventions. 50 years ago, nobody had thought that we will have a mobile phone. Or 200 years back, we never had an idea that we will fly in the air or something like that. So, it may look funny or foolish or silly, but everyone has to think on this point and see that every one of you is a Vishwakarma. So, only that thing has to be brought out, and for the society, for the mankind, we have to work for that. So I must congratulate him for all these very impressive presentations. Thank you very much.
Thank you. Just wish to add one point what Chairman sir said. Sir was mentioning that there should be easily carryable building off the shelf which can go to their home, respective homes, and they start using it. We have actually started this bit in school buildings, wherein we have modeled two particular different models, which are basically like 6 packages weighing approximately 24 square meter of building, approximately weighs around 350, approximately 300 to 400 kgs, and around 80 square meters of building is approximately 900 kgs, 940 kgs. And these buildings can be carried, as you mentioned, it can be carried in auto rickshaws or on their shoulders to remote places where those places are inaccessible. So we have done it. Of course, it's a bit towards what Vishwakarma has done, but we have certainly started out.
It's a mini Vishwakarma, but that yet appears.
I request Avinash Shirode sir to honor Amit Kabade with a small token of love.
In last year, we participated in PEPSCON as a audience, and then we thought, why not go for precast, which is the next evolution after AAC. Block to bring up the contractor segment is also a very unorganized sector in India. So we thought to organize this sector and build to bring precast solution in India. And in a short period of time, last year, in a short period of time, in 5 years, we have done 100 crores of turnover. This year, we are expecting to do 150 crores of turnover. Magic Creek is funded by private equity Motilal Oswal in 2013, and this is our capability. We have a nationwide presence in north, east, west, south, all zones of India. We have three plants of AC block manufacturing in India as on date, and we are planning to expand in southern India and eastern India also. Then we have diversified into dry mortar segment also, which is also a green product. It don't require curing. For example, the mortar which is being used in India earlier, it requires curing, and the mortar which we are selling with the AC block doesn't require any curing. So it's a green product. There is a less consumption of water, and you can also control the quality of the product. The third division which we diversified into is precast division. We started this division last year, and I would say we have done considerable efforts to develop the division. I'll share the details. And magically it was identified in Forbes India as hidden gem of 2014. These are few of the picks. So I would like to take this opportunity to share the efforts we are doing for the Swachh Bharat mission of India. So actually we have designed toilets with precast, and in Andhra Pradesh we are building 500, almost 1100 toilets with precast and brick and mortar also, where accessibility is an issue in almost 500 schools. We have already started this project and almost covered 100 schools as on date. We started last month only. And these schools are in remote villages in Andhra Pradesh. We are working from Guntur district to East Godavari district across Andhra Pradesh. So these are the total sanitation facts in India as on date. We require, as per our Honorable Prime Minister, almost 11 crore toilets are required to be installed by 2022. And almost there is a shortage of 1 lakh toilets, girls' toilets in school, because of which there is a dropout of almost 23% in girls' student size. So the idea is to build toilets for schools, toilets in schools for girl students. And this is a condition which is existing in schools as on date. The toilets are not being maintained, they are poorly constructed, half of them are in broken condition. People are not using toilets at all and urinating or sitting in the open areas. So need of the hour is to build the toilets which are easy to install, easy to clean, low maintenance, no foundation, so that it can be easily erected, durable, secure, strong, and definitely it should have a proper ventilation. So this is the solution which we are executing as on date. These are few of the images. This is just an implementation approach. It has been broken down into elements, and then we are unloading that with the help of a movable gantry at the side and installing them with a wall shoe arrangement. This is just the sewage part, so which is also precast. And these are few of our customers from AAC, which buy our AAC material. Apart from toilets, basically we started precast to do building projects, and the toilets just came in our way, and we are proud to contribute to our nation in building toilets in India. Apart from that, we have also done an erection. We have also backed a project of 50 villas in Surat. So I'll just play a video of what erection we have done. We have set up a precast plant in Surat, western part of India. So when we started manufacturing AAC, there were only 3 plants in India. Now there are almost 80 plants. What magically did, it took the product, which was initially a very niche product for real estate sector. We took it to masses. So this is the same which we want to do with precast. So we have started that revolution, and I hope we will be successful in that. And I would like PEPSCON to do such events in western and northern India also. Okay. Thank you. Thank you. Thank you.
This session will be on contemporary and spaceplate technologies for high-rise shell and core and land span roof construction. I request Dr. M.S. Sudarshan, Secretary General, ACC India, to please occupy the chair on the dais as the chairperson of this session. And I request Srinidhi Anantharaman, Director, Geodestic, to occupy the chair on the dais. He completed BTech from RECW Warangal, passed out in 1981, Civil Engineering, and Masters of Engineering Science from Sydney University, passed out in 1984, Structural Engineering and Construction Management, founded Geotechnics 1986, and his passions are technology solutions for design and build and urban transport. I request Srinidhi Anantharaman, sir, to give the presentation.
Over to China. Very good afternoon to you all. I welcome you all for this wonderful session in the afternoon. I'm sure Srinidhi will keep us awake after the sumptuous lunch. I would call Srinidhi a complete professional because he is the one who has brought in new technologies, who was involved in the analysis, was involved in the design, was involved in the manufacture of elements, was involved in the fabrication, installation, erection. So that way I would call him a complete professional, and I'm sure we are going to have a very good presentation by him. Over to Srinidhi.
Thank you, Chairman.
Srinidhi, we have about, the session is for 45 minutes. Maybe you can take 40 minutes, then another 5 minutes for questions and answers.
Excellent. Can everybody hear me? I can't move my any closer to me. Okay. As we said, my passion is technology solutions. I've always been in design and build. And the other area which was a more recent, you can say, acquisition was urban transport, which I will not dwell too much upon, but there are some examples here and there I will just tell you. A brief history of the company. We were set up in 1986, and we are considered one of the reputed, kind of design and build companies in the engineering construction. Sorry. Okay, we have been doing these innovative lightweight solutions for a long time, and that's where we started. We built a lot of steel, glass, concrete, and fabric structures. We had clients ranging from Infosys to TCS to Nuclear Power Corporation. We were very, very good clients, and we have always looked at alternate techniques against the traditional construction. And we have actually sort of, you can say, defined what is called architectural engineering, structural engineering, and construction engineering. Because otherwise there is a tendency for people to think of engineering only as structural engineering. And the word architectural engineering actually was coined in very early days by us, but I understand that several universities are now offering degrees in architectural engineering, so that's a very interesting thought. And one of the things we will talk about a little more in length is the mobile terminal 2, which have been very recently inaugurated, as a matter of fact, last year. So that's a very, very interesting project. Some of the other things I'll briefly touch upon is the Delhi airport and the Bangalore airport. Very broadly, if you look at it, we have this kind of an ecosystem, which is the owner-developer who appoints architect, engineering consultant, who also appoints project management consultant, typically appoints an EPC contractor, who in turn brings in suppliers, specialist subcontractors. When I say specialist, I mean design and build subcontractors, and who also has his own share of PRW, piece rate workers and labor contractors. This is broadly the kind of ecosystem. This is where we have been. Practically all our lives, you can say. Then the other part I want to very recently, just don't get too caught up with it, but it's more important to understand the flow. We have design, I deliberately put design first and then analysis, though many people tend to think it's analysis and design. But there is no analysis without design. Design is actually the hypothesis, analysis is the test to see whether your hypothesis is right or wrong. So it's always a case where the design is done first. And in fact, I remember in my University of Sydney days, we were taught to actually size members without analyzing. We had to start by sizing the members. We had to do, hand calculation, whatever you may call it, and then check whether we were right or wrong. So that is the one which sort of helped us gain confidence in our ability, and our intuition started building up. But nowadays what is happening is people tend to sort of look at STAD as the primary thing. See, STAD has a small design engine, but it's primarily an analysis engine, or for that matter, any other engine. But the trick there is, once you get caught into that forest, you see trees all over. You don't see anymore the whole forest, the entire picture. So that's why I prefer to use the word design first and then the analysis. Design is more about form, function, flow. Whether you're talking about flow, stress flow, or people flow, or wind flow, it's all about design. Similarly, function, what's the functionality of what you're doing? I'm not trying to distinguish anywhere between architecture and engineering here. Design is a very broad thing, because form is determined very often by architects, but form has a very significant role in the engineering part of it. Next is analysis. Everybody knows loading, boundary conditions, and sizing of members. The real engineering, if you may call it that, this is also engineering, I'm not denying that. But when you talk about this engineering, this is where you're starting to touch upon construction engineering. You're talking about connection design, you're talking about detail engineering, you're talking about 3D modeling of the structure, you're talking about a lot more things which generally in the last ecosystem, the previous slide, this tends to be done at this level. Sometimes here, but more often at this level it is done. So it is not normally touched upon at this level. Okay? So that's a very important stage. There's connection design, field modeling, and interfacing also. When you have a lot of clients with a lot of other agencies, you have to figure out how exactly what is the thicknesses they are providing, what is the kind of detailed seating that you have to provide for that. Next important thing is planning. Planning is where the most important aspect of methodology comes in. I'm not saying this happens later. I'm just saying that gets defined at that point. Planning would have been happening right from the beginning. You'll be thinking about methodology, constructability, even at the time of design, even at the time of engineering. But this is where it gets defined. It actually gets established. After that, we have the procurement, which is the critical thing where you take out quantities and you establish exact quantities, nesting and things like that. Ordering, receiving materials. This we're not going into too much. I mean, there is a body of technology available when you think of products like SAP and all that, but we are not going to go into that too much, except quantity surveying does play a role for us. Next is prefab. So I'm sure in yesterday's session and today's session, people have spoken enough about prefab and precast for that matter. We would like to distinguish between these two just for the sake of order more than anything else. We use the term prefab when we are talking about steel. We use the term precast when we are talking about concrete. And these are the two big words in front of us. These are two elephants in the room, you can say. One is prefabrication, the other one is precasting. Sometimes people use this interchangeably, but it's better not to create confusion. It's better to have prefab to represent steel, precast to represent the concrete. In steel, typically you have a process, if you look at it, cut and drill is the first process. Of course, if you are looking at things like reinforcements, that would still come under precast, that would come under what is called cut and bend. Here we are talking about cut and drill. That is cutting plates, cutting sections, drilling them. These are pretty much automated. Then there's this fit up and weld. That's a very, very important next stage of the process. That is generally manual. Unless you do repetitive things, yes, you can have robotics and stuff like that. But normal, our construction industry, we are making unique things every day. So there is really no way you can automate it. But we have made an attempt. I'll just show you some examples. Then we have this pre-bar. This is a technology we have developed. I'll just dwell upon it a little bit later. In terms of precasting, we have something called preform. That is, it's a formwork-based system exactly. Then there's rebar and then jackstack. At the construction level, we have once you deliver, you assemble, you lift. This is what I'm only talking about the domain of precast and prefab. I'm not talking about general construction. General construction, there is tiling and all that. I'm not talking about that. I'm talking about the technology part, the shell and core part of it. I'll come back to this slide a little later for any questions. What we have been focusing upon is trying to look at what are the emerging areas. One is affordable housing. office buildings, wherever you go, I'm sure Vijayawada is a prime candidate for that, but this has been a problem in other cities also. Hotels, hostel buildings, bridges, skywalks, airports, metro terminals, there's a whole gamut of them. We have been trying to see what are the commonalities that technologically that we can provide for these kind of applications. The common problems, this I think most people may agree with me, is reliance on scarce, skilled manpower. This is the problem India is facing. Gone are the days when labor was cheap. Labor is not cheap. On the contrary, labor is expensive because they are not skilled enough and you don't have enough of them and you face a problem. The next thing is the higher cost of labor, plant and equipment, farm work, all these things are generally becoming more expensive. So these are pain points. The next one, if you look at it, most construction, during the process, there is a lot of degradation, environmental degradation. If you look at bricks in the old days, topsoil used to get affected. If you look at sand-based, concrete-based construction, there's a lot of sand, which is it's a scarce resource, and people are not wanting to use sand so much. If you look at anything, even the construction process, when you have 600 people on a project site, you have an environmental degradation. There's a lot of debris being generated. It's generally messy. The construction process is a bit messy. So that's a pain point as far as we concerned. Slower slab cycles, speed of construction has always been a problem. So I address all these as pain points. Okay. The last one is the lower quality due to non-industrial practices. What we mean by this is you do everything one-off. Fourth floor is done only once. Then you go to fifth floor. Whatever problems came, it remains buried in fourth floor. Then you go to fifth floor, it's a different set of working. Whereas industrialized construction, if you look at manufacturing and all that, there is a cyclicity going on there. So even if you don't get it right, by the time you come to the 10th or the 15th iteration, it starts to become better. Okay. So looking at the conventional structural system, this is just a little bit of background. What we have RCC beam column, which has been very, very popular. I think all of us are getting here together to see what are the alternatives to this. This pain points used to be weak beam column junction, labor intensive work, need for masonry walls and plastering, excess debris. Everybody knows about it. I don't need to say much about it. Then the next, really you could say the interesting thing was flat slabs and flat plates. They are pretty good. You get both RCC type systems as well as pre-stressed concrete. But they have some issues of their own. They cannot be core cut so easily. The cable profile is always suspect. I'm not sure whether you are so aware. When you look at many of the flat slabs that are being done, extremely thin slabs, 200 thick and all, you're always a little bit uneasy about the cable profile. So there's a little bit of an area of gray area. Higher vibration, because of the fact that you're making it thinner and spans are larger, we do have vibration issues which has to be addressed. Of course, sand usage is there. It's thick. Comparatively, if you had a beam column, the equivalent slab thickness might have been 150. But a flat slab, the equivalent slab thickness will be 230 or 240. So you are putting in more mass. So automatically the foundation becomes heavier. This has its own share of debris. Yes, it's a far improvement over this. Masonry construction is the most traditional one. I do want to mention it because for villas, even today people are following this. They require again skilled labor, which you are fast running out of, and all the usual kind of problems. What are the contemporary structural solutions? If you look at it, I think what has really become popular today is monolithic construction. The other one is precast construction. Monolithic, everybody knows by its trade name. I think people refer to it as Maiwan construction. It's like Xerox copy, it's a photocopy. But this is the generic name. Monolithic construction is the generic name, where you cast the wall and the slab monolithically. It's a fantastic technique, no doubt about it. It achieves this very important on-castable rigidity. That is very, very important from a structural point of view. It eliminates columns, beams, masonry walls, and definitely allows faster slab thickness. What are its share of problems? Formwork capex. The capital expenditure for formwork is very, very high. Plus, they are not modular. So if you have an apartment building and the design changes, you have to reinvest in the formwork. Yes, people have tried to reuse the previous one, but it's a nightmare. It does generate debris. Any Maiwan project site or monolithic project site you go, you see a lot of debris around. Rebar is very labor intensive. I have put this picture. It's a very, very labor intensive process and it's messy, particularly because there's very little reinforcement. If you had more reinforcement, it would be self-standing and all that, but this has its own set of working. Formwork is the most labor intensive because what happens once you cast the slab, there's no crane access to it. So you have to dismantle it manually and take it to the side and again take it to the upper. If you look at precast concrete, it's God's gift to construction industry. There's no doubt about it. But what is its share of problems? Of course, I'm talking about three types of precasting. One is a beam column type, the other one is a large panel type, which is what I saw magically showing the video when I came in. And the third one is a pot type. In large panel type, you have entire walls and slabs being panel, and the pot type, an entire room is itself precast. So that is what we mean by the pot type. It has got a few problems, not many. One is the transportation cost. Second one is, in a beam column system, the junctions are a little suspect. People have never been very comfortable, particularly structural engineers, in terms of the beam column as well as the slab wall junction. People have tried to achieve it, but at the end of the day, it is a problem. Unless somebody finds a way to bolt it. In fact, one of our initiatives is actually to make bolted precast construction. So which we will use structural steel analogies and try to do them. That is one thing which we are attempting. But without that, we do have some issues, basically. Higher investment, definitely higher heavy site drainage. Without that, this is something we have to deal with. So what are the modern structural systems? What we call geodesic structural systems. We don't own it. But at the same time, what I'm now going to talk about is specifically ours. But there is a generic solution to it also. One is what we call a quad space frame. Now what we mean by the quad space frame is essentially a steel building, but it has some interesting techniques built into it. So it makes it as efficient and as modular and as industrial as the conventional space frame. So I will just dwell upon that a little bit later. And if you look at it, this is now, you can say applying space frame to multi-story building. Okay. So this has its distinct advantages: large column free spaces, faster construction. It does depend on deck slabs and drywall. It's not drywall, it's drywall. It is highly amenable to automated production. It doesn't require skilled labor. I think this is something which is very, very important. We don't need skilled labor in this case. Okay? Minimal sand usage. So this is one family, but the equivalent of this generically is a steel building. This is a very important development which we have done, which is what we call the space plate system. Now in the space plate system, what we have essentially tried to do is take the advantages of precast, take the advantages of monolithic construction, but throw away the disadvantages. That's why I went on the previous slide there. Combine monolithic construction, combine precast technology, and added some additional ingredients to it. One important ingredient we have added is what is called pre-bar technology. What is pre-bar? It's a brand name of a bar, but it is essentially prefabricated rebar cage. Now, there are varieties of things. People are used to it. It's not anything new. If you remember pile reinforcement are always supplied like this. Very often you see even on project sites, they will tie the rebar down below into large cages and then lift it in position. It's something like that. But we have taken a patent and there are some very interesting developments we have done. But I don't have time to dwell on it. What is important is, when we talk about the reinforcement cages, we are now prefabricating. We are engineering this. The same way we have to engineer structural steel, we are going to engineer this thing, and that makes the whole process much faster. You don't have one fellow tying bar by bar kind of thing. So this is something which we are trying to do. The other thing is the preform form. Now I want to just tell you one very important difference which I explained to you. Once you cast the slab, you don't have crane access. So we are deliberately not casting slabs. What we are doing in the space plate technology, vertical elements are cast in place, horizontal elements are precast. Why? Horizontal elements, when you cast in place, the cycle time is very long. You have to leave the shuttering. There is a nightmare. Everybody knows that. Environmental. Even a little chacha is a very thing to actually cast. So we want to take anything which is horizontal as a precast in variety of ways. There's one building we are doing, it's a 40-story building, we are using only hollow core slabs. Vertical elements can be cast in place because it's brilliant. Within 6 hours, 8 hours, I mean, there are people who will be doing this water treatment plants and large water tanks. Walls are very, very fast to cast, and there are a lot of wall casting technology. And you cast the wall, you have the opening on the top. The crane can come and pick up the crane. So we have large gang formwork. We don't have little pieces of formwork we have dismantled and taken off. So that's the advantage of the space plate system. Wall is a single core. Wall preform and Zaxplan. Zaxplan is essentially a partially precast slab. I have some pictures of that. It's easy to provide conduit. So why we are using partially precast and not fully precast is because there is a lot of activity which happens at the slab level. You know, the conduits, radiant cooling, there are so many things. You know, if there's a toilet, then you have to have some kind of plumbing down below. So all these things cannot be done if you have a fully precast thing. Even the sunken slab, all these things can be eliminated if you have partially precast. Partially precast advantage is the soffit is nice and clean. At the same time, it's not fully cast, so you don't require heavy equipment. We limit our panel sizes and panel thicknesses and everything, such that we are not dealing with more than a standard tower crane tip load or a standard tower crane, depending on the kind of layout. We will plan maybe 2 tons, 2.5 tons, maximum 3.5 tons. If the building is compact and very tall, it will be larger. So, important thing is modular formwork. The same formwork has now become modular because we are dealing with only, you can say, a plant dimension. We don't have an elevational dimension anymore. We have a plant dimension. We don't have all this slab formwork to be put in. So that's the other advantage. It is considered to be economical. Okay. Just before I go further, I just want to tell you broadly how we have approached the construction industry. We have 3 platforms essentially. One is the space frame platform. This you can think mentally like a steel intensive platform. These are all steel. Then we have on the other side space plane, which is a concrete intensive platform. What we have in the middle is a software which binds this whole thing together. The software that is design, analysis, engineering and planning. We have this GeoSuite is basically a software. I don't want to tell you too much about space frame. I think everybody knows about space frame, what they are. Essentially a 3-dimensional kind of structure behavior. We've got a lot of text in it. I don't want to go into it. Our system, we have something called a skull space frame. What was the thing was normal space frames are pin jointed. So they are a little bit, everybody here are engineers, so you will understand. Pin jointed space frame, you can't apply lateral loading and there are some inherent problems. So we took out actually patent quite some time ago on skull space frame, and that's what we actually have developed further on. Now, if you look at skull application, this is more interesting. So this is one which we took a patent for many years ago. This is a single board which holds 12 members together. This, of course, the patent is expired, anybody can do it, but that's the thing. This is actually the skull, one of the variants of the skull node connector. This is another skull node connector. These are all skull node connectors. Okay? And it is being used in very complex geometrical shapes. Okay? One very good example we would like to talk about the Koramangala Indoor Stadium and the Bangalore Airport. Koramangala Indoor Stadium, because it is a reasonably large span, 55 meters or 80 meters. It's a curved geometry. It has got concrete decking on top of it. And it was back done, I think, in 1995. Quite some time ago, but it's interesting in the terms of using it because this particular node connector gave it partial rigidity. Normally the space frame nodes which are spherical nodes don't give rigidity, they are pin jointed. This gives partial rigidity. Subsequently for the Bangalore airport we developed a kind of an extension of the skull system where we got full rigidity. So these are again skull nodes, but these are very heavy rigidity nodes, and the other thing is where normal space frames are single boards, now we have multiple boards. We have 8 boards, 16 boards connecting members. So this makes it much more sophisticated. Here again we use this improved skull node joint system. Here the advantage in the Bangalore thing is the geometry is complex, but we were able to industrialize it, we were able to modularize it. Quad space frame is what I just very briefly spoke to you about. This is a little boring because it's essentially interconnection of beams and columns. Everybody knows about it. But probably the difference we have put into it is we have made it automated. The design is automated, the fabrication is automated, only erection is actually more or less the manual way. But then again, there are some interesting techniques we have used there. These are classic applications of the quad node system. This is of course what we did for Jindal, this steel structure. What is important to note here is that this particular thing was completely hands-free. From the time we developed the basic architectural engineering geometry till the time of production, there was no input of data. There was absolutely no input of data other than what came through the system. It was always completely system driven, right up to the DSTV files, right up to the kind of the NC code and the production itself, drilling. And in this we eliminated welding. That was one of the important, because welding is an expensive process in India. You can't get, welding should be used very carefully, very selectively it has to be used. It cannot be used ad hoc, because welding is expensive, it is slow, and you sometimes have serious quality issues. This is another building which we have done using similar concept. Here is again a job which we tried. It's a typical pre-engineered building, but we used techniques similar to this. That is, we automated the actual process. One more thing I would like to just very briefly talk about. People are used to pre-stressed concrete. We have done one project with pre-stressed steel. This is the thing which we did for Infosys, and it's actually what is called external stressing, and we have developed the kind of deviator systems and all that. So I'll be more than happy to talk to anybody if there is a need. What's the advantage of this? Reduces the deflections, it reduces the steel consumption, and it's a very realistic. See, structurally, one problem is there. Strength, grade are about 350 megapascals, whereas rebar is 500 megapascals. So already there's a losing battle. So RCC also, that's the reason why RCC is generally considered more cheap. Only nowadays people are finding other issues with it. But by combining post-tensioning with structural steel, we are again able to sort of increase the strength. Space plate advantages, I have very briefly spoken to you about it, because I don't want to dwell upon it too much at this particular point in time. One very important thing is, yes, there is a distinct time benefit to it. It combines a model construction kind of thing. I will just now go for the next 3-4 slides. I will not dwell too much in detail. This is one thing I just want to talk to you about. When I mentioned this brief on the jack span system, here if you notice, it's partially precast. In the US, this is called the filigree slab or something like that. So the advantage of, see, this is the radiant cooling pipes that are being made. You can lay conduits, you can do anything you want here. So this is the advantage when you're particularly doing multi-story buildings. You can do precasting, but at the same time you don't have to pay the premium of precasting. This is the hollow core slab which we are currently using for a 40-story building I spoke to you about. This is quite interesting. I'm sure people would have spoken to you about this yesterday, so I don't want to go over it once again. But it's an excellent material. Only thing you can't lay conduits with it. This is the point I just spoke to you about prefab automation. This is a robo, but it's the robo not used for welding, but it's used for cutting, plasma cutting or oxyacetylene cutting. This is another machine which we have, which actually mass produces. It drills the hole in 3 orientations, the 2 flanges as well as the web. It drills concurrently, and it's very, there's hardly any people. There's just 2 operators who operate it, and it's got excellent production, very reliable. You don't have to drill it manually and things like that. It's completely conveyor belt kind of system. But these things to use best, it has to be done in such a way that the design itself promotes the use of it. This is another robot. This is a coping robot. That is, if you have sections at the end of the eye section where all you want to take out things, you want to make some detailing, if you may call it that. This is an 8-axis robot. This is 7-axis robot. This is an 8-axis robot. 8-axis is the job itself moves around in that direction. This is a multi-torch machine where you can cut very, very large plates before they go into the next stage, which is this. This is a beam builder. This is particularly useful if you're doing bridge girders or if you're doing tall shear walls, which you want to do composite shear walls and things. This is excellent because this particular thing can make a beam which is 2.6, 2.7 meters thick, 80 mm flanges. So it's a very nice machine. Fit up and welding I spoke to you about briefly. These are jobs which we have done. If you notice, it's a very complex welding and fit up. Everything is in 3 dimensions. This is incidentally the Mumbai airport. And it's complex. I don't know how else to put it. And this is quite difficult. So we have tried to automate it to a limited extent. But we have a bogie system which goes around. But having said that, it comes with its own thing. We try our best to eliminate it. Avoid fit up and welding. If you cannot avoid it, yes, you try to use this particular kind of. So this is an example. I'll just show you a little bit later. The other part of this whole business is what is called heavy lifting and launching. The one example which you see here on top, if anybody is here from Mumbai, they will know about the Milan ROB. That is a 60-meter column-free span built over the busiest stretch of railways, probably one of the busiest stretches of railways in the world. It's not about 7 or 8 tracks below, and every minute, every 10 seconds there's one train or the other going. So this was actually done by us, and this is a temporary support. Actually, it's 60-meter clear span, but we have this temporary support here. And this is a 6-lane bridge, by the way. So this launching is a very interesting technique. So that is something which we have actually over the years mastered, and this is essential. If you want to look at the whole process, as an engineer, you need to know about architectural engineering, you need to know about launching. There's no way you can get away from it. If you don't know, then there is something wrong with it. So this is another thing which I will again talk to you very briefly about on the heavy lifting and launching kind of thing, where we actually sort of move 250 ton, you can say, assemblies, which were 100 feet by 100 feet, the size of a 5-story building. We moved it on a 55-meter column-free span bridge. This was a separate project, you can think of it. The bridge itself was a separate project. I'll just got examples of that. I'll just go over the project because this is where much of what I'm talking about is better illustrated. probably sometimes better to show the projects and then talk about this. This Google will fall asleep perhaps. Okay. But having said that, I'm hoping somebody will wake up now. These are all the jobs which have been done by us. I mean, this is the one which we did for Infosys back in, I think about 7 or 8 years ago. It's a 100 meter by 60 meter by 40 meter dome. Single layer dome, one of the largest single layer domes. In fact, this might be of interest to you. Largest single layer dome in the world. Okay, people cannot do single layer dome. Prior to this, we had built one which was 60 meters in the Nirmal extent. Also a single layer dome. Generally, when you have very, very large diameters, you have to create double layer because otherwise you don't have the structure in them. This is another job which we have built for Infosys. It's a large multiplex. This again job for Infosys. We have done a lot of work for Infosys actually. One interesting job we have done, Metro Cash and Carry in Hyderabad. This is based on the space frame system. It's dual modularity. If you look at PEV modularity, linear modularity, you can only add in one direction. In this, theoretically, you can add in both the directions. You can grow in both the directions. That's what the beauty of it is. This is the most recent example of space frame where we have used it for dome. This is a 90 meter diameter dome. This is a 60 meter, I think. A 49 meter barrel wall. This is the barrel wall, which is 49 meter. It's quite interesting. Nowadays, these are becoming popular because I think Supreme Court they have said that any open coal storage and all has to be kept covered. And all that. That's how this is started. This is a very nice job we have done in Nagpur for the Boeing for the hangar. It's two spans of 100 meters each. Two adjacent spans of 100 meters each. Mind you, these are pretty heavy duty because the truss itself is 9 meters. And the middle of the truss depth is equal to a 3-story building, so it's a fairly large. I think one of my passions was mentioned very recently, particularly in terms of urban transport. Monorail stations, the Mumbai monorail, we were the consultants. We actually wanted to be involved in construction, but for various reasons we couldn't do it. Because we couldn't actually convince the clients to go for steel. So it ended up being concrete and we ended up being consultants. But we have done all the stations and the depot. And we have also concurrently developed what is called the elevated busway, which is fantastic in the sense that it is 1/5 the cost of metro, 1/3 the cost of a monorail, and ideal for cities. No doubt ideal for tier 2 cities, definitely also ideal for tier 1 cities as feeder system. Okay? This is one of the passions. This is a very nice job I'd like to dwell upon a little bit. It's the Mumbai International Airport. This is a 33-acre structural steel roof. It involved 21,000 tons of steel. This was featured because it's very, very interesting. I got that. Thank you. It was featured in the Discovery Channel. On one hour program, particularly because it was quite an exciting erection methodology. But it had a whole you can say background to it. Everything in this was, you can say, really, really complicated. But beautiful. Structure was absolutely beautiful. Our tender submissions, how we were going to erect it. Because, most airport roofs, the departure level slab is large. The roof comes on top of it, you can't run cranes on it. And it's not the smaller airports, okay, but these are very, very large airports. The Delhi airport also is similar. So you have to come up with innovative ways of actually doing the erection. In this case, this is a running airport. Mumbai was a running airport, so it's as good as trying to do some heart surgery on somebody who's running. It's really like that. And microsurgery or something like that. You had serious problems doing that. So they gave us a 3/4 acre of lay down area. We proposed that we build a tower here. These are the columns on which the actual pods rest. And these columns, just to get an illustration of size, this column was 2.5 meters by 2.5 meters cross section. So just to get an idea, and they're swinging right from the ground. We assemble these pods. These pods are 100 feet by 100 feet, just to get an illustration of it. Assemble it here, move it along this on bogies, and lower it down on top of the columns. This was the proposal which we gave them. So this is how we have done it. And this comes prefabricated from a Beaver factory, gets assembled here and relocated. We won the job. These bridges are all temporary bridges. They are not permanently there. That itself was a separate project. So this was the way it was done. Actually, these pods get interconnected. In one direction, the span is 34 meters. In the other direction, the span is 64 meters. So in both the directions, there are infills. What is called infills? The pods are interconnected. adding to that, there was a further complication. This particular area, there was a Shivaji statue, which for various reasons they could not move for 18 months. Civil engineer's life as it is miserable. But further misery is added by these kind of political issues, which just leave us with, That's why we have to be problem solvers, because there is a whole army of people creating problems. So we need somebody, right? So this is how we get pulled into this thing. It always comes finally to the civil engineer. Okay, this is the final thing. So this is the structure. I have a video. If I have time, I'll show it to you. Are you sure? Okay. It will be quite interesting actually. I will do the talking. There is some talking which happens here. Just snippets of it. This is the first portion of the structure.
The top each of the mega columns, spanning 105 feet out from the center in either direction. The pods transfer loads laterally and then down each mega column, allowing engineers to remove 30 mega columns.
This is a demonstration of flip permit. This is a demonstration of flip permit.
4,000 individual steel segments. This unprecedented rail system allows crews to move structural caps, called pods, atop all 30 megacolumns without blocking access to the shrine below. Once the roof is finished, this entire 1,270-ton structure will be taken apart, making it one of the largest temporary structures ever built.
This is a demonstration of flip permit.
Eight-sided steel disc called a bogey. Using two hydraulic pistons that act like arms, the bogey grabs onto rails that run atop the highway truss, pulling both itself and the pod forward. But with only a narrow 36-foot base, the trick is keeping the 100-foot wide pod in balance. With the blessing ceremony now complete, the crew prepares to move the bogey.
This is a demonstration of flip permit.
Pulling with over 30 tons of force.
From here you can really understand.
Each stroke takes 4 minutes, moving the pod just 5 feet forward. Crews repeat the process 75 times over the next 4 hours before reaching the peak.
That movement took about an hour to span. The normal movement was 34 meters. The first span was 54 meters, 55 meters. That took about 1 hour, and it had basically a bogie which had 20 skid rollers, 10 oriented in north-south direction, 10 oriented in the east-west direction. It had jacks behind them, and these jacks were actually balancing. We were completely monitoring the jack, the pressure in the jack, so that you should not tilt, because if we go 100 feet, it's only on a 30 feet base it's moving across. Then we also have to make sure that it takes a turn, because some direction, some distance it moves also, then it stop at one point and turn. So there what we did, we lowered all the 20 jacks, then removed the east-west jack, so north-south is now engaged, we move around that particular direction. We had this push-pull cylinder, they have shown 2, but they actually had 4. So we wanted to sort of move it to take it to the turning, to remove the push-pull and put it on the side. We had another set of a pair of push-pull behind to make sure it doesn't run away. So all the kind of concern we had. It's a very it's an extraordinary engineering feat. It's as good as moving a 5-story building on a bridge. So that kind of thing. This is a slightly better illustration. This is our own video. This has more sounds. Just to give you a scale of what we are talking about. This is the pod which is under on the tower which is being erected. You see the size of the person. Then you get an idea in terms of what it is we were actually moving in that particular place. And this is quite unusual or extraordinary from an Indian point of view, because there have people in concrete world, a lot of people have done this kind of, I'm not saying this has not been done, but this two-dimensional movement has not been done. See, this is has gone up to here, then it's turning. And finally when it goes on the column, all the 20 skid rollers get engaged, then we lower the jacks gently onto it and we make the final adjustment and hold it. That's how this particular thing is. These are some snapshots. This is how the construction was in our bigger factory. We actually assembled 4 of them in the factory. It's so large, it didn't fit into the factory assembly. This sort of make sure. This one element which is going inside the pod, the central element, this alone weighs 62 tons. It is a very large fabrication. This is the inbuilt process. These are some of the details. All these are automated details. It's not actually manually drawn. They are completely automated details. I know so there might be some representative of Tekla here, but we did not use Tekla for this. We used another engine, our own in-house engine. Of course, we could export it to Tekla later, but this was done in-house. These are some of the kind of connection details which is quite interesting. Very, very complex, three-dimensional. We had plates of up to 100, 120 millimeters which were being welded together. I'm not saying this is the best of design. In some ways, this design was endured upon us. But our mission is actually to avoid this kind of design, to see if we can make it more constructible. If at the design stage, if you start thinking about these kind of things, then you start looking at better ways of doing this. Some more images of that, miscellaneous work and things like that. I don't want to dwell too long on this. This is our factory I've already shown you about. Oops, I've come to the wrong presentation. Where that was. The same input process. Some examples. The Bangalore airport, which some of you would have probably seen, quite interesting. It's a very free-form kind of structure, but at the same time, we needed to find a way to modularize it. There's an east expansion and a west expansion, which looks symmetrical, but is not really symmetrical. Heavier structural details are different. Every truss is unique in this. At the same time, we had to find a way to mass produce those trusses, because there are quite a few of them. So there was an original architectural grid of 8 meters by 8 meters. So we made the entire thing in such a way that every intersection of the grid, we introduced a vertical node and created trusses, lattice trusses in both the directions, which will be exactly welded onto this vertical node. And the trick here was the trusses themselves, the only parameter that changed apart from the section. See, sections can be automatically fabricated in our shop. The final problem is really fit up and weld. So we had one parameter, which is the elevation difference between the right hand side and the left hand side. There's a skew in it. So that was the only thing. So we built a kind of a jig by which we could automate that process and achieve it very, very fast. There are some images during the construction. This is another very interesting job we have done. This was done about 6 years ago. Delhi Airport, it's about 22 acres of it. This was a pure design and build kind of job. Here again, we assembled on the departure level slab 1.5 acre segments, weighing 650 tons, which were lifted up through a 16-point synchronized lift, which is a highly computerized kind of thing. Because when you start lifting, you need more than 3 points, because you are introducing an indeterminacy. So you will not be aware of what kind of stresses you are inducing in the structure. Anything more than 3 points. 3 is okay. 3 forms of plane on a bigger process. The moment you have the 4th, you don't know. The 4th might be pulling it faster than the other 3. So there's the issue that comes up. So we had to lift 16 points in one shot. So we had to make sure once the jacks, the pressure were maintained, all 16 went up absolutely in a synchronized. I have some videos of that also. So these are again large in the sense 1.5 acre segment which were actually lifted up. This was on the land side. On the air side, we had other complications because we didn't have a clear departure level slab. We had mezzanine slabs and all that. So there what we did was we built an entire scaffold. So we assembled in parts at the bull nose, but in the tip of the structure, we assembled 18-meter segment, pulled it in, added another 18-meter segment, pulled it in. Finally, the last pull we were pulling in 120 meters. Again, it had become a 1.5 acre segment which was pulling in. So that was what was done in the Delhi airport. Why I am sharing all this is, it's really nice to know the whole process. I myself, in my heart of hearts, I think I'm a structural engineer. But these things are also actually part and parcel of structural engineering. If you really look at it holistically. This, I think there is some images. This is a very nice building which we have done in Angul. It's a 12-story building. This is pure steel intensive residential building, which is quite rare, and we were given an opportunity to do some development from later. So this was one of the outcomes that came about it. This combines several technologies, which is definitely not homegrown. The only thing which we can claim fame to on this is the quad space frame kind of system. Rest of it, there is the Schnell wall system, which is actually an Italian development. Then for the slabs, there is this what is called speed flow. The speed flow actually is a New Zealand technology. It's all been invested by Jindal, so it is quite nice in the sense that we're able to integrate a lot of it. We've had our share of troubles. This has not been an easy process because some of the things happen very fast, some of the things really got slowed down. The Schnell wall technology depends on gunniting. So gunniting is notoriously slow, particularly at higher levels and all that. So we had some share of problems in that process. This I mentioned this a little bit earlier. This is this is a pure steel building. The slab is only concrete, everything else is steel. This is another job which is opposite building. It's a 16-story building done in Mumbai. This is a very nice job. I thought maybe just very briefly talk about it. This is done for TCS in Sirusay, Chennai. This has got this, it's got 6 buildings on top of which there are the mini spines which are measuring 120 meters each. Very complex. Then in the bang in the middle there is what is called a central spine, which is 405 meters long and it is about 50 or 52 meters tall. Entirely welded. Totally welded, there is no bolting. That's what the architect wanted. This is another view of it. It's quite an extraordinary, it's like a sculpture you can say. This was developed by a South American architect. And we were fortunate to actually have been selected for this particular job. It is quite complex in many ways. The way it was done, I mean, from the erection point of view, really large sub-assemblies, partially fabricated down below and taken on top and fully welded. This is one of the processes that is being done. This is how we visualize the main, this is called the main spine structure. This is how we visualize it, this is how it was built. And in this setup we had, this is where we actually first invested in the robo, because profiling was so complicated, every member is unique. Actually there's a quarter symmetry, one quarter similar to the other quarter. Quadrant A similar to quadrant C. But I will not do it together, so I have no benefit from that being similar. Every piece I have to do it uniquely. So there's no way I could do it in the normal way. So we invested in a robo, we wrote a software so that the robo could do the profile. So that's how this entire thing was done. Of course, welding was done conventionally. Bending was also done. This is a very nice job we have done. Actually, we have done only the engineering for the job in Singapore called Gardens by the Bay. This we approached it in a different way. This, what happened was this has a certain kind of, you can say a DNA for how the structure is generated. There was a certain architectural intention involved. So what we did was, instead of trying to use it the normal way, develop the detailing in Tekla, creating the model and all that, what we did was, because we knew the primitives, we wrote a software to generate the entire drawing. First time we didn't get it right. Then we tweaked it. Finally we got the software. It took us about a month to develop the software. But after that, it took us 15 minutes to generate the drawings. So any number of iterations we could do. So that was the interesting thing about it. And this was good because Singaporean people pay well for this kind of services. Not in our country obviously, but so it was worth the kind of effort. But we do have this software. We have a lot of such software, which is not completely general purpose. It's based on building typology. If we get another building on this typology, we can do it. But it's not generally, it's not like a general purpose computer aided design. It's more like a computer automated design. That's the difference between what we do and what you have. A lot of general purpose software. With general purpose software, you can draw an almirah, you can draw interiors, you can draw buildings, you can draw anything you want. Our software we can't. If there's a software, it can only draw almirahs. It's an almirah software. There's another one which can only draw buildings or only domes that way. But the advantage for us is there's a lot of artificial intelligence we can build into it. Whereas in the general purpose, you can't build artificial. This is some other job. I will now run through quickly because we should give a little bit of time for questions also. So these are some of the skywalks. I think many of the skywalks in Hyderabad has been done by the way. Done and dismantled also because the metros come and this and that has happened. Skywalks have a life of their own. They keep coming up with it. So this in a way wraps up my presentation for the afternoon. I hope I have been able to cover and have done justice to the topic. Thank you very much. Cross section, one arch is a trapezium, the other arch is actually a 6 hexagon shaped thing. And what is the funny thing about this arch is going from one end to another. The original, the architectural intent have been done in such a way that they were warped. I don't know whether you visualize that. It's like, all such large arches have to be built up from plates, cut to shape and welded together. But if you don't engineer it from the beginning properly, you will end up with twists and kind of, like a dalda twist. That's the best example. Always dented and all that. So that was the problem that had come about in that. What the architect shared with us was this. He gave us this particular, it's a torus actually. He gave us this, not a torus, sorry. I don't know, it's some special name he gave for this particular shape. He shared with us this shape. He said how he has achieved the geometry is by cutting a portion of it. You should notice that it's being cut off here. So we took this particular geometry, and that's what I was telling you about the software which we wrote. There were two things, there's cool dry and cool moist. The two domes if you notice in the Gardens by the Bay. So in this, he gave another geometry. This is slightly more parabolic. So here again, he gave us the basic geometry, the functional geometry, and how the arches were sliced and how the main structure itself was sliced. So using these two as the... Oh, I don't have the rest of the thing. Using these, we actually wrote the tool and we generated this kind of connector system and this particular geometry, this particular arch, that is the built-up section, how the entire thing is assembled together. And we wrote a small little, you can say, algorithm to make sure that we eliminate the twist. That means we start from one end and we use only planar surfaces. That's the same thing. 3 points form a plane. The fourth point you position it inside that plane. So now you've got the 4-point plane. From the 4-point plane you go to the next piece of the plane. You're actually cutting this out of 12 meters by 3 meters place. So you're actually generating the geometry. That's what we did for the arch. So here, this section also is odd. If you notice, this is the grid shell. The grid shell cross-section of members itself is odd. And these are again welded structures. So we developed the entire detailing, the profiling for the members to get connected. Fabrication was done by Singapore. Similarly, in the other case also, that is square. This is square. Is this again a node connector, but it's a welded node. So this is just about kind of. Okay, I hope this answers. One more?
That arches is solid, sir.
No, they are hollow.
Hollow.
They are consisting of plates.
What size?
Would be roughly about 4 meters, 3 meters big. They are quite big.
And the width?
These are all 120, 160 mm big. These are very dense, closely spaced. These are
Glass is stuck with this.
glass panels are fitted on. No other question?
Yeah.
Yes.
We had shown some big frameworks like 45 by 60 meters like that. They were taken on the track and inserted on the top of some columns and all.
Bombay.
So what is the column structure and how it is?
It's a steel. Column is also steel. It's a cruciform section. The column itself is a cruciform section. That means it's a 2.5 meter deep I section with 2 T's attached to the other. It's a cruciform. It's a symmetrical section.
And it is again encased with...
Finally encased. Encased in a circular. That's what you see in Mumbai.
So once your software generates the geometry of each separate element, which seems to be different from the other, in field when you weld them, don't they need to be held together at the exactly right angle before you weld them, etc.?
See, in this case, what was done was these were welded in the factory in Somerset. See, Singapore, the beauty of Singapore is you can carry prefabricated panels which are 11 meters, 10 meters wide. So these are assembled at the factory in large panels. These panels are taken and finally interconnected. In fact, what I am not emphasizing is the whole board of temporary work design. This is what when we refer to construction engineering, we mean that also. So there, what happens is, it's not just the permanent structure, there is an entire temporary structure which is also engineered, which is also fabricated and detailed to the same precision. Only then we get this particular shape. And within the factory, we had again temporary work support, and we had this roll station for getting the 3D coordinates. So that's how we achieved this activity.
What about the trees?
That was not done by us. No. We did our share of plays in Bangalore airport, but those plays were nice actually. It was a lovely job, not done there.
Lifting technology that we are seeing nowadays, right? Now, precast in industrial structures has been happening across the globe in Europe and all. Now, yesterday, precast has also shown us for some of the industries where they have shown this process also in concrete form in a curved manner, and then it has been happening even into that, not only in the building sector, right? So it is now time now for precast in building sector, where we are focusing through this particular PEPSCON conference predominantly, right? So precast per building. Precast, when you look at it, an industry, wherever you look at it abroad or even here, if you look at something like this, at some location they will be casting the columns, beams, walls, and then the slab like this, right? The concept of precast, as all of us know, is a prefabricated construction, include those buildings. There is a confusion, as Srinidhi rightly said. Let us think prefab as steel or precast as concrete, if we have to clear our minds. But NBCC code has clearly said that it is prefabricated elements, like it be concrete or steel, right? So it is a majority of the structural components which are standardized and produced in plants in a location away from the building, and then they are transported to the site for assembly. Right? These components are manufactured by industrial methods based on mass production in order to build a large number of buildings in a short time at a low cost. That is how the precast. Now we know the advantages, right? The factory condition production, and it is all weather working. Whether you have rain or cyclone, whatever it is, you can keep working inside, right? Better quality, finish, accuracy could be done. I have got an inquiry some time ago from Indian Navy people. They said they have about 35 kilometers long boundary wall. I have said to them that precast is the best solution. You can't keep on transferring your formwork all along 35 kilometers long. Please cast it at one place. This can be simply transported everywhere, erected there. There is a type of solutions which we have to give, which is easier and they give it, right? And it is less labor, less wastage, less cost. This is how it is. You can see some of those precast this thing, and you can see much more into this. The limitations. Limitations are suitable for certain applications is what people will say. Of course, it has cost and viability depends on volumes, logistics, okay, productions. Logistics are production, handling, and placement. Our roads must be good for the transportation also. Flexibility of openings and cutouts, okay, and connection detail method, design integration, high equipment intensity, damage or breakage during handling and placement. Tax and duty structure is centralized facility. Tax is one thing which is hitting this precast development in a very bad manner. We have been trying to represent the government in various levels to get these tax reductions into the structure, and we'll appraise you on that. When you look at the cast system, let us look at the system, how congested it is with all the formwork, especially in a structure like Mumbai, where you can see that the whole formwork is there. How can the people stand and work there? Which is a very, very difficult thing to run. When you look at precast, is there a formwork at all? There is no formwork at all. Everything is made as a frame. It has come into the building. It is fixed there. That's the beauty into the precast system that we are going to. Precast abroad, you just see where I have spent about 10 years time in the Gulf. Much of these buildings have, the claddings are also with the precast, right? There is no brick masonry or anything else. Neat facade will come and get fixed there. When hollow core slabs will go into the structure. Much of these structures which have come as a mushroom type, right from 2000 to 2010 in Dubai, which is a wonderful period of civil engineering construction with the boom. There, prior to 2000, there are about 3 precast companies. Thereafter, it has become about 12 precast companies. Even 12 precast companies could not sustain to the type of construction there. Even cast institute construction has also gone in. Even Burj Khalifa structure, what you are looking at, they have not taken precast into the structure at all, because they fear that precast companies are already heavily loaded, they will not be able to do